Welcome to Study Loop.
Hello everyone, thanks for joining me today. Today we're going to be looking at the concept of work and kinetic energy. And what we have is two springs. One is a linear spring with a force to displacement relation of the force equals 3 kilonewtons per meter times the displacement. And then we have a nonlinear spring where the force is equal to 3 kilonewtons per meter times the quantity x plus 160x cubed. What we have is a mass that is 5 kilograms that is placed on top and released from rest, allowing the spring to compress. And what we're asked to find is the maximum displacement and the maximum force of the spring. So first thing that we're going to do is draw a free body diagram to look at the force that are acting upon the spring. So we're going to draw the box first, and we have, as always, a weight force acting down, and we have the spring force acting up. Now, by using Newton's third law, each force has an equal and opposite force. So when we draw the free body diagram for the spring, we can simply flip the directions of these forces acting on the block. So we have a spring force acting downwards, and we have that same weight force from the block acting upwards. And for the sake of the argument, we are going to define the down direction as positive x. So we know that the block is starting from rest, so we know that the initial kinetic energy is 0. And we also know that the maximum displacement will occur when the kinetic energy of the next point is 0. So the kinetic energy at x max is 0 because that is where it's undergoing the maximum acceleration, and that is going to be the furthest distance away from equilibrium, and that is going to be our maximum displacement point. So in short, the maximum displacement occurs at t2 equals 0. Now this simplifies our computation a bit, because now all we have to worry about is the u term from 1 to 2, and that is the work done on the block from 1 to 2, or the spring from 1 to 2. And following convention, this is going to be equal to 1/2 ky squared. Now this is the energy in the spring, due to the spring, minus the energy from the weight of the block. Let's make these x's. And again, this will be equal to 0 just because t1 plus u12 is equal to t2. But as shown here, t1 is 0 and t2 is 0. So all we're left with is the u1 to 2 term. So we have that 0 equals 1/2 kx squared minus wx. Now this is a pretty simple equation. We just have to solve for x. Remember that we know what k is, it's 3 kilonewtons per meter, and we know what the weight is, that is simply mg, where m is the mass, which is 5 kilograms, and g is the force of gravity. So this yields us a x max distance of 32.7 millimeters. And this is going to be x max for the linear spring. Now we're also asked to solve for what is the maximum force applied by that spring. So we know that F max, just due to Hooke's law, occurs at x max, which we have just solved for, right? Because we know that F max is equal to k times x max. Now remember, we know what k is, 3 kilonewtons per meter. We just solve for x max, and this gives us a maximum force of 98.1 newtons. Now we're going to move over to the nonlinear spring. So again, the same argument holds. The kinetic energy in the beginning is 0. Kinetic energy at the end is 0 because x max also occurs when the kinetic energy is equivalent to 0. So now we can write out the expression for the work done by the spring force and the weight force. So now we're going to have an integral because this is a nonlinear spring. So we have to integrate to solve for the work done by that spring force. So this is going to be equal to 3,000 x plus 160 x cubed dx minus the work done by weight. Remember that Wx is outside of the integral. So plugging in for the terms that we know, we can actually bring this 3,000 out because that's a constant, so that's going to be 3,000 integral from 0 to x of x plus 160 x cubed dx minus wx. Luckily for us, this entire term expression is equal to 0 because t1 plus u12 is equal to t2, and as I said before, t1 is 0, t2 is 0, so this is all equal to 0. Alright, so now what I'm going to do actually is bring this wx over to the other side of this expression. And that enables us to say wx equals 3,000 times the integral from 0 to x of x plus 160 x cubed dx. Alright, so now we just have to simply evaluate this integral, so we know that wx equals 3,000 times x squared over 2 plus 160 x to the 4th over 4. And now we're just going to plug in for wx. Since we know what w is, that's simply mg. We can say mgx equals 3,000 x squared over 2 plus 40x to the 4th. Now, as you can see, this is just a simple equation that we have to solve for x. That is our only unknown. We know the mass is 5 kilograms. We know g is acceleration due to gravity. And solving this for x gives us an x max of 30.4 millimeters. So that is the maximum displacement. Now again, we also see that the F max occurs at x max. So what this means is we just have to plug in this x max that we found here into our equation for the force. So to recall, the force in this nonlinear spring is equal to 3 kilonewtons a meter times x plus 160 x cubed. And you can see just from this expression that maximizing this x maximizes the force. So by plugging in the x max that we have, we simply get an answer of 104.7 newtons. And that is our final answer.